This video on differentiation introduces differentiation for GCSE students. It wouldn't be suitable for A-level students. It basically just deals with gradients and maximum and minimum points. So here's a graph, and the equation of the curve is given to us there as half x cubed plus 2x squared plus 1. And imagine I'm interested in the gradient, the slope of this graph at the point where x is -3, which I've marked on there. So that would be the point we're talking about. What was the slope, the gradient of the curve at that point? Well, to find an estimate for that gradient, I could draw a tangent. That blue tangent there just touches the curve at the point where x equals -3. And if I find the gradient of the blue tangent, it will be an estimate of the gradient of the curve. So between those 2 points on the blue tangent, in the y direction, it's an increase of 4.2. In the x direction, it's an increase of 3. So the gradient at x equals -3, that's approximately equals to 4.2 over 3. That's approximately 1.4. If I wish to find the gradient exactly at that point, I would differentiate that equation. Now, simply differentiation is a rule that will give us the gradient of the curve. I'm trying to keep this simple, not getting too complicated. It's a little bit, well, quite a bit more depth than I'm going to give you, but here are the bare bones, as it were. First of all, the expression for differentiating y with respect to x is called dy by dx. That's how you would say it. It's not a fraction in the real sense, so we can't cancel these d's down. It's not dy divided by dx. It's just an expression. Okay, and what it means is the change in y, that's what the dy stands for, the change in y divided by the change in x, and that's why it gives us the gradient, because of course the gradient of a line is the change in y divided by the change in x. So the rules for differentiating, let's try and apply the rules. So 0.5x cubed, you bring the power of 3, the cube, down to the front and multiply. So that becomes 3 times by 0.5. And then you reduce that power of x by 1. So the power of x was 3. It's now being reduced by 1. So it's 2. And 3 times a half x squared is 1.5x squared. Let's apply it to the next term, the 2x squared. When you differentiate that, it becomes 2 times 2x. Where do we get that from? Well, the 2, the power, is brought down to the front here, so that's the 2. 2x is, originally we had 2x squared, we reduced the power by 1, so 2x squared just simply becomes 2x. So that term simplifies to 4x, and when you differentiate a number, a constant, you get 0, so we don't have anything once we differentiate. So when we differentiate that curve, that's the expression we obtain for dy by dx. Now we want to find the gradient, or we wanted to find the gradient when x was -3. So we simply substitute in x equals -3 into our expression for differentiation. So it's 1.5 times x squared, so that becomes 1.5 times -3 squared, plus 4 lots of -3. And that works out at 1.5. Now you may remember from the previous slide that our estimate for the gradient was 1.4, so it wasn't a bad estimate. 1.4 was the estimate, but 1.5 is the actual precise gradient of the curve where x is -3. Now what about when x equals 0? If we look on the actual curve, and I'll put the dot here at x equals 0, okay, down here, and if I draw the tangent to that curve, i.e. the line that just touches the curve, I get a perfectly horizontal line. Now the gradient of a horizontal line is 0. So the diagram is suggesting to us that the gradient of this curve, where x is 0, is going to be 0. Well, let's see. dy by dx, which is, let's look up here, is 1.5x squared plus 4x. If we put 0 into that expression, 1.5 times 0 squared plus 4 lots of 0, we do indeed get 0. So the gradient of the curve looks like 0 when we drew the tangent, and actually when we calculated it, it is 0. So let's differentiate this expression. I'm going to go through the rules of differentiating. So dy by dx, remember that's what it's called, dy by dx. So that first term, we bring the power down, which was 3, and times it by 5x squared. Remember, we reduce the power of x by 1, so 5x cubed becomes 5x squared, and that 3 came from the original power which we brought down to the front. So 3 times 5x squared is 15x squared. Apply the same rule to subtract 7x squared, so we bring the power down, so we end up with subtract 2 times 7x. It's 7x because we reduce the power by 1, so 7x squared, when we reduce the power by 1, becomes 7x. So that simplifies to minus 14x. When we have an x term, we simply end up with just plus 8. So we lose the x, and plus 8x, when we differentiate it, becomes plus 8. And the constant on the end, you may remember what happened to the constant last time, that just disappears altogether. So here's a second expression. We're going to differentiate that, just to go through those rules again. 6x to the 4, we bring the power of 4 down to the front, so it's 4 times 6x cubed. Remember, 6x to the 4, we reduce the power by 1, so it becomes 6x cubed. And that simplifies to 24x cubed. The second term, we bring the power down, so it's subtract 2 times 3x. 2 was the power we brought down. And when we reduce the power by 1, 3x squared becomes 3x. So minus 2 times 3x minus 6x. Remember up here that plus 9x, sorry, I beg your pardon, plus 8x became plus 8. When we differentiate 9x, it becomes plus 9. And the number on the end, the constant on the end, when we differentiate, just is lost. Okay, so those are the rules for differentiating. Now, we can only differentiate powers of x for the time being. So if we have an expression which looks like that, where we've got x outside the bracket, we have to multiply that bracket out before we differentiate. We have to write our expression as a powers of x. So we've got powers of x and powers of x here. Once we've got an expression written as powers of x only, now we can differentiate. So when we differentiate x cubed, the 3 comes down to the front. We reduce the power of x by 1, so we end up with 3x squared. And the minus 12x, when we differentiate, becomes subtract 12. In our second example, once again, before we differentiate, we have to write this expression in terms of powers of x. So, first of all, 2 over x is the same as 2 times 1 over x. And similarly, subtracting 3 over x squared, well, 3 over x squared is 3 times 1 over x squared. Now, my expression as written here still isn't in terms of powers of x. I'm going to do that now. 1 over x is x to the negative 1. So timesing that by 2 becomes 2 times x to the negative 1. 1 over x squared is x to the negative 2. So 3 times 1 over x squared is 3 lots of x to the negative 2. So now I've written my expression as powers of x, I can now apply the rules of differentiating. So bring the power down, so that's negative 1, and then reduce the power by 1. So 2x to the negative 1 becomes 2x to the negative 2. I've reduced that power by 1. And that simplifies to negative 2x to the negative 2. For the second term, when I differentiate it, just be careful. I've got the subtraction there, so I still keep the subtraction. Then it's negative 2 brought down, okay, times by, and that's 3x to the negative 3. So that simplifies to plus 6 lots of x to the negative 3. This next section on differentiation focuses on maximum and minimum points, so let's explain exactly what they are. At a maximum or minimum point, the gradient is 0. So on this point on the curve here, where I put the little mark on, we draw a tangent to the curve at that point. We can see that that's a horizontal line and the gradient of the curve is 0. Similarly, down here at this point, draw the tangent to the curve, the gradient is 0. Why are these maximum and minimum points? Let's look at the maximum point first. The curve is increasing, reaches that point and then turns back down again. So at this particular point here, in this area, in this neighborhood of the curve reaches its maximum point before coming back down. As it comes back down, it reaches this point and then it turns back upwards. So in this area here, this blue dot would be the minimum point on the curve. Now that's actually the equation of the curve. So let's differentiate and see if we can actually find out what these values are. So applying the rules of differentiating, bring the power down and reduce the power by 1, and that simplifies to 1.5x squared. For the next term, bring the power down and then reduce the power by 1, so 2 times 2x is 4x, and the plus 1, when we differentiate, just disappears. So that's our expression for dy by dx. That will give us the gradient at any point on the curve. Now for a max or minimum point, we want dy by dx to equal 0. So we put the expression for dy by dx equal to 0, and we solve that equation. We get x equals 0, or the bracket must equal 0. So 1.5x plus 4 must equal 0, and that gives us those two values there of 0 and negative 8/3. So we have a look at our graph. 0, that's one turning point, and negative 8/3, that's the other turning point there. If you want to find the corresponding y values, then we substitute the x values back into the original equation, which is what we're going to do in our next example. So we want to find the minimum point on the curve y equals 2x squared. Just a point to note, quite an important point really, because this equation has got positive x squared, the curve for this will be a U-shaped curve. If that was a negative x squared, then it would be an N-shaped curve. The point about it being a U-shaped curve, if you can picture a U in your mind, it's got a minimum point where the curve turns, okay? So let's differentiate. 2x squared when we differentiate, bring the power down, that becomes 2 times, and then we reduce the power by 1, so it becomes 2 times 2x, that's 4x. Minus 8x when we differentiate becomes minus 8, and the plus 1 when we differentiate disappears. For a maximum or minimum point, then dy by dx equals 0. So 4x subtract 8 equals 0, and that gives us a value of x equaling 2. And in order to find the corresponding y value, we substitute x equals 2 back into the expression here for y. So 2 times x squared becomes 2 times 2 squared. Subtract 8 times x becomes subtract 8 times 2. And then the plus 1 on the end gives us a y value of -7. Therefore, the point 2, -7 is the minimum point on the curve. And if I show you a graph of the curve, that's what it looks like. It's U-shaped, and there is the point 2, -7, the minimum point of the curve. In example 2, this time we want a maximum point. The reason why it will be a maximum point, we've got a negative x squared. If our quadratic equation is a negative x squared, it's an N-shaped curve, as you will see in a moment. We differentiate the equation of the curve. Minus x squared becomes minus 2 times x, that's negative 2x. Plus 2x differentiates to just plus 2. And when we differentiate 5, it disappears. We put dy by dx equal to 0 for a maximum or minimum point. In this case, it's maximum. So negative 2x plus 2 equals 0, and that gives us an x value equal to 1. When x equals 1, we substitute that back into the expression for y in order to find the corresponding y value, and we get a y value of 6. So 1, 6, according to our calculation, is the maximum point, and in actual fact, that's the curve there. And as you can see, that is the point 1, 6, which is where the curve turns. Here's a recap then of the main points. Differentiating gives us an expression for the gradient of a curve. When we differentiate a power of x, x to the power of n, we bring the power down n to the front, and then we reduce the power of x by 1, so that would leave us with a power of n minus 1 in this case. To find the gradient for a particular value of x, we substitute that particular value of x into the expression we have for dy by dx. For a maximum or minimum point, dy by dx equals 0. And once we have found the x value that makes dy by dx equal to 0, we substitute that value of x back into the equation for y to give us the corresponding y value and hence the actual coordinate of the turning point.